report, so you've got all of this as well. Right, as a reminder, if you haven't yet opened SPSS, this is how you get it. And I'll show you the way you can do it from home or any other computer, so that if you're outside of this lab, you can still access SPSS. I'll show you on the, just want to double check, yeah, it's captioning. Okay, go to your, if you've already opened SPSS, don't worry about these steps, but if you haven't yet, follow me along. So if any browser you like, go to your student zone where you access everything for your studies. It might ask you to log in. And then here under IT resources, you've got a button for remote access service for students. Open a browser. Tell them no thanks. IT resources. Remote access service for students. Great. Okay. When you're on, have you got it? Yeah. Cool. When you're on that page, and to catch up with the class now, there's a link here somewhere in the text that says Apps Anywhere. They've hidden it quite nicely for some reason. That's just what they've done. So you go click on Apps Anywhere, and that will take you to a login page that looks like this. So from here, type in your usual login credentials for London Mets. So whatever your username and password is, don't say it out loud. Okay. On your computer at home, if you're opening it for the first time, you can install Apps Anywhere. If not, if you already got it, or like now you already have Apps Anywhere, just say I have it already. It's on this computer, and now you've got Apps Anywhere open. So Apps Anywhere, like I said last week, is sort of like Netflix for applications. It streams applications. So there's a computer somewhere in this building that is running all of these programs. You're remotely controlling that computer when you're using Apps Anywhere. So it means you're streaming the program instead of downloading it, which is a huge advantage because things like SPSS are massive, big files, and you don't want that sitting there clogging up your hard drive and you're slowing down your RAM and that sort of thing. So this is it's a nice solution for that. Now, it does mean you can't work offline, which is annoying. If you, like me, like to work on a tube, then you don't have to work on something else. I try to get IT to give me access codes for things, but they never do. Stick to your work hours. Anyway, when you get to this page here, we can find SPSS by going SPSS like that, and you've got two options. So use SPSS statistics, not SPSS AMOS. AMOS is used for like weird regression analyses that we aren't ready for. So let's click SPSS statistics and launch. And you may get that validation question. It'll say we're validating da 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 da. You just press yes or okay or please validate, so whatever it asks you to do throughout the process. And it should open like that. Have you got that? Is it working? Yeah, great. It says what? It is the temperamental nature of these computers. you've got it, you've got a couple of them open, so you might want to close some of those, otherwise you'll end up with all sorts of things. Okay. Alright, so that's how you get into SPSS, and we'll just say we'll open a new data set, and then we've got as a brief reminder, this is a blank SPSS sheet. This is our data view. When we import our data, this is where we'll see it. All of the raw data will appear into this grid, and our variable view allows us to control all the aspects around our data. It makes the rules that SPSS will use to apply to the data when it analyzes the work. So we will, you remember last week we used this to shift things around a little bit. So from WebLearn, you have access to the data sets. If you go to learning materials and either week 7 or week 8, it's the same stuff. There's a folder called SPSS tutorial, and then you've got this one here, the .sav file. SPSS.sav. So go to your if you have SPSS open, you can open the .sav file, and you should get the class data. It's this one. I'll come and show you. Wait to find it. It's SPSS tutorial, and then the last one on that list. SPSS tutorial, yeah, and then that one. Yes, perfect. So click on that one, and then it'll download it and open that, and then that'll be your data. Okay. Have you got it? Got it. You're already doing your analysis, you're 3 steps ahead. Fantastic. You need to open WebLearn. Go to your module. Alright, so as a reminder, what is the purpose of our coursework reports?
To test the hypothesis.
What is the hypothesis?
Whether the student's energy intake is different to energy expenditure.
Okay, very, very important point. So the main question we're trying to answer in this report, and the thing you're building your whole report around, is that question, is that are these students you in energy balance or not during those 3 days of data collection?
Good question. When we do the introduction, because the data for mains were taken off the main list.
The what?
The data for the guys.
Yes.
Was taken off that. Should we mention it or should stick to?
I'll show you where it's mentioned. It's just in that first paragraph.
Alright.
Set in the results. Yeah, that's fine. Weirdly enough, it's the strength of the data, but I'll tell you about that. I'll tell you why that is. Something against you gentlemen, it's just the way it is. Yeah, wait, okay. And then SPSS tutorial. And then this last file there. So you can open that, double click it. And there you go, there's your data. Cool. Okay.
These 48 materials in the library and anywhere else.
Really? All right. So the first main point is that your whole report is going to be built around the research question, and you've just done a coursework support, so I'm sure you're well clued up on what you're meant to be doing, and you have an idea of the structure of the report. It's in the structure of a scientific report like any other lab report you write. So you'll have an introduction. The methods you kind of forget, don't worry about that. You can just say refer to the module handbook, and then the results and discussion. Your introduction is usually providing background information up until the end where it gives you a research question. So there's that PowerPoint slides over here, and I think this also, the same information that I'm showing you now is in the coursework booklet. So, sorry, let's just enable editing there. So your introduction should end with this statement. Okay, so write your introduction, and then the last thing you write for your introduction is the aim of this report is to identify whether a cohort of students are in energy balance during the period of time studied. Don't worry about your similarity report for that. We've given you this thing. We expect you to have it in there. That's not a concern, right? Everyone's aim is of course the same because you're all doing the same experiment. So, aim of the report. So have that at the end of your introduction. You'll see that in any fairly decent scientific reports. So if I show you on this one, which is what I want to do today that is slightly different, can you see this? There's this article with its introduction, blah blah blah. It's giving you all the background stuff that you might want to know if you're going to make sense of the report. And then it gets to the end, and the last thing before we get the method, so the last part of the introduction, this study aimed to do that. So the last paragraph in your introduction should be your aim. Okay. Things to think about for your introduction is tell us about energy balance, because that's crucial for understanding the research question. What is energy intake, expenditure? What is some of the methods for assessing intake and expenditure, especially focusing on gold standard methods? Can you remember what's the gold standard for energy expenditure? Water, great.
Wait, diary.
7-day wait food diary for energy intake.
Yeah.
For energy intake. Okay, if you've explained that in your introduction, great. We'll come back to that idea later on when we talk about the discussion. So you're building up and you're setting up all the stuff that someone who is intelligent but not necessarily an expert in energy balance might need to know to understand what is it exactly that you did here. Okay, so that's the focus. Your introduction builds up to the aim, and then you give your aim, and you've got your aim. Right, so that's your aim there. The aim is to identify if we're in energy balance. And you remember last week we had this hypothesis. Now, you will never really see hypotheses in actual scientific reports. They're kind of background stuff. They're doing your calculations, right? That's your rough work. That doesn't actually go into the final polished report. So don't include the hypothesis in your main report. Just the aim is what we want to see. And we'll assume that you are working from hypotheses. So the way hypothesis testing works is it's very particular to statistics. When we want to demonstrate something, we will test hypotheses. And you see that we've got two hypotheses there. You've got a null and alternative. The null hypothesis is always associated with no difference, no association. There's nothing special happening there, and nothing interesting. It's just there's no difference. So our null hypothesis is that the energy intake is not different to expenditure, that our students are in energy balance. And remember, what is the energy balance equation?
Energy expenditure. Intake plus energy intake equals
Energy input equal energy output.
Yeah.
PR equals
You're all very, very close. Okay, if what is the thing that changes if you're not in energy balance?
The weight.
Weight. Yeah. So you could say energy intake equals expenditure plus minus change in body stores.
Okay.
And whatever that's the general equation. There'll be slightly different versions of it. So that's a nice thing you could include in your introduction, because it helps you understand, well, what do we do here? Okay. It helps us interpret the result we get. So here what we're saying is, for our null hypothesis, the student's energy intake is not different from expenditure. In that sense, if we think of it in terms of the energy balance equation, intake equals expenditure plus 0 change in body stores. They're not gaining weight, they're not losing weight, they're just in energy balance. We're testing to see, are they in energy balance. So what we want to do is, based on our data, how likely is it that class is actually in energy balance? Yeah? We're going to test the probability of this. So if our probability of this null hypothesis turns out to be really low, we say, actually, we don't think this is the most likely thing to happen then, so we'll reject this. And instead we'll say the intake is different to expenditure. Probability is, the alternative is true. And the implication of that then is, think of your energy balance equation. They might be losing weight or they might be gaining weight. Okay, so you start to see how the whole report starts fitting together, from the introduction right through to your conclusions perhaps. But this is our hypothesis. This is what we're testing. So when we do the t-test later on, that's the statement we're testing. We're saying, how likely is it that they are actually in energy balance? P is less than 0.05, which is the cutoff for statistical significance. We say there's a less than 5% probability that this is a true statement. So less than 5% isn't really making us very confident that that's true. So we'll reject that then. As we did last week when we did the test, we said that they are different. So we can think about the implications of that. Alright, happy there. Has anyone got any questions up to this point? No, all fine? Yes.
In your introduction, go into more detail what included energy expenditure, like physical activity level, thermodynamics. Would you elaborate on all that?
Yes. Thermodynamics. Sorry, I've been speaking for 2 hours.
Thermal energy, like how 20% alternate is 10%, or 10%?
No, yeah, definitely. Talk about the energy balance equation,
Yeah.
because that's fundamental to understanding this. Talk about components of energy expenditure, because you've looked at basal metabolic rates. You've got your physical activity that was calculated. So components of energy expenditure is important. Thermodynamics really important, because that explains how the equation works. This is the law of conservation of energy and the conservation of mass. If you eat less than you expend, that difference has got to be made up from somewhere. That's the second law of thermodynamics. So having that explanation in there helps us to understand this whole thing. Like I said, you're writing for maybe the intelligent non-expert who doesn't see how all these pieces fit together. And then talk about the different methods for actually measuring this stuff in humans.
So the Douglas bag.
Yeah, you can talk about like indirect calorimetry.
Resting metabolic rate, no?
Yeah. I would probably focus on the gold standard methods, because you've only got so many words you can write. You could talk about indirect, and then we use prediction equation here, so that's maybe something to include. Yeah. And then you've got all the ingredients you need for a beautiful introduction. So if you follow that, you should be good. Okay, shall we do some descriptives? Shall we do some descriptive statistics? Okay, if you remember last week, we did this. So go to your data set. there you can see we've got all of our nice variables. In data view, you've got all of the actual data. And we can take a look, we can see there's energy intake for everyone's energy expenditure, all in calories. And keep that research question in mind. Are they in energy balance? If we take a look at this first person, 2,256 calories intake, 2,719 expenditure. So we sort of suspect that person is not in energy balance. They're in negative energy balance, according to the energy balance equation. Again, look at number 7 there, 1,936 intake, 2,450 expenditure. So another one in negative energy balance, right? What we're going to do is explore to see not the individuals, but as a group, is that same pattern, do we observe that on average with the whole group? So for that, go to Analyze and go to Descriptive Statistics, so the button from the ribbon there, Descriptive Statistics and Descriptives. And there we can add all of our variables. Can you see there's the little ruler with the energy intake? If you click on it, highlight it, and click the arrow in, it'll move from our list into this kind of action box that SPSS is going to do. So we can move all of those in, and once you've moved them all in, you can press OK. So the only one you don't want to move in is Analyze, and then Descriptive Statistics, and then so you kind of stay open and now move all of those variables into there. So 6 like that one. You did it last week, so you know that. Alright, once you've got all of your variables in, you can press OK, and then you'll get the SPSS outputs. Alright, so we've got it doesn't let me zoom in, which is really irritating, but there you go. You'll have the same results as me on your page. Now let's think about presentation, because you've seen these results last week, so they shouldn't be surprising to you. The first thing is SPSS tables are really ugly. Look at it, horrifying. Don't want to see it. If I see it in your reports, I get really upset, and that's just no good. So make your own tables with this information.
I don't mind this table.
You don't mind this table.
I don't mind it either.
You're making it for me. I want to see it. I know you can do better than this. If you tried to submit something like this to a journal, you would have an editor crying, saying, "What have you done? Why have you done it like this?" You make your own tables from here, and if you can learn to make them really nice, then all of your other coursework will go really, really smoothly. So a few things to note. Most of these are quite alright, they look good. You know, your headings for the variables are all there. They've got units. Kilogram per meter squared could probably be cleaned up a bit. Doesn't look great. But the rest, that's fine. Valid N list-wise. Is there any information in that row that is valuable to us?
No.
Get rid. Don't want it. Leave it out. Hello, Shadi. Welcome.
Yeah.
Do you want to do this? Do you want to come in and do some stats?
Thank you.
No
Yeah,
problem.
I would, sorry for are you putting
I'll see you later. Yeah, email me. Right, wait. Valid N list-wise.
Did we remove the ends from that column as well.
You can. Yeah, look at that. It's so repetitive. 67, 67. Huh?
How do you take it out?
You make your own table from scratch. So that's why I was saying you need to don't present the SPSS table. They're really not great. Make your own table, insert that information into it. Okay. What I would say though is you should report the sample size in any result that you have. Okay, so remember last week I showed you this PDF file. Where is my PDF file? So firstly, so I've got this PDF. This I can zoom in, so I can make this a bit more easy to see. Remember to start your results with a paragraph like this, explaining how did we get from the total originally collected data through to the number of final participants. So you can see we've got 67 participants, which is the same as the number on your descriptives table. Okay. So that's good. So have a table like this. Maybe clean it up. I wasn't too bothered about being very poetic writing this. Okay, it's not presented nicely. If you take a look at other studies, then you will see much nicer versions. So here you can see the same in this article. Total sample was 2,396 infants, 690 participants removed, missing data, these ones for implausible values, and then duplicates removed, and you've got the final sample. So it's standard practice to have that as part of your scientific writing. If you get this right now, you'll have no problems at all. I think you'll probably find the same in this article here. Again, 9 records removed, and further 10 removed for incomplete data. So you generally would start your results saying, how did you end up with the final amount? The next thing to do is start giving your descriptive results. And you can see in this article anyway, you've got things like, well, there's the ethnicity, you've got the male-female split, so we said half the sample were male, and then the mean and standard deviation for the age was 9.7 months, with a standard deviation of 6 months, and you've got the sort of descriptives for some of the outcomes that we're looking at. Alright, the reason those variables are described in this article is because, one thing, it helps us to understand who were these people. So we have slightly less information about our sample in your experiment. For example, we don't have things like ethnicity. We don't have the age of participants. Okay. Sometimes that's nice to include because it sort of gives us a picture, okay, who are we talking about here? In this article, we could say these kids are all, on average, 9 months old. So I know I'm talking about a toddler, someone who's really, really young. They're probably not moving around too much on their own yet. They're probably sort of in that complementary weaning stage. So there's a lot of information we can assume or we can imagine about that group, that sample, just from that information. The other thing is, if we think about this article and its aims, right, where's the aim? So the aim of this study was to describe malnutrition risk among these young children in this place. So malnutrition risk is the outcome. And then in the results, one of the first things they tell you is about these markers of malnutrition risk. Can you see the pattern emerging? So they're saying, I'm interested in malnutrition risk. Here's some scores that explain that descriptively. If we take a look at your results, okay, from this table, from this descriptive data, you have a mean energy intake, you have a mean BMR, energy expenditure, weight, height, those sort of things. Remind me, what is your research question?
Correlation between energy intake and
Yeah, so energy intake and energy expenditure. So if I was going to provide the reader with the key descriptive statistics, what do you think those would be?
The energy intake,
Mhm.
energy expenditure.
And energy expenditure, simple as that. Yeah, it's once you see the pattern, this becomes very, very easy and very straightforward. So, what our reader would like to see, or what we want to present to our reader, the information that's going to help them understand what we've done as fast as possible, to answer the question as fast as possible. So, once you've done that little paragraph saying this is how we got to the final sample, give us a short, maybe 2 sentences, describing the key descriptive statistics. The average, the mean energy intake for this sample was 1,825 calories. And the mean energy expenditure was 2,402 calories. That's it. You can say the standard deviations, of course, got them there. Maybe you want to talk about minimum, maximum, whatever you like. But those are the key results from this table. Those are the main things that we're interested in. And it contributes to the story we're telling. Because then the reader can immediately see, 1,825, it does appear to be different to 2,402. And then they can anticipate. Yeah?
So we are going to just talk about the energy intake and energy expenditure. We are not going to give example of height and weight or talk about anything else. Just
Don't have to, no. I would focus on those two as the key things. Yeah.
Maybe BMI.
You can if you want, yeah, you can highlight stuff. But I would say as a minimum and possibly optimum, at very least talk about energy intake and expenditure.
yeah, the results should be just this one. But discussion we can use that BMI.
No, not in the discussion. Have it here. So have that little short paragraph saying here's the main results from our descriptors, intake and expenditure, as shown in table 1, and then give us this table, your version of it, the nice version, the pretty version,
Just one
the one you
table
made yourself.
yeah? You have just one table.
Yeah, this one. Okay, and then there'll be other results that you'll present. We'll get to those. But always refer to your figures and tables in the text. So you have the paragraph saying here's the average energy intake as shown in table 1. So it's referred to in the table, and then give this its own name, its own heading. And we should, if these researchers were any good, they would have exactly that. You can sort of see it. So I know this is table 1 and table 2 they're talking about, but can you see that as illustrated in table 2, and then gives you some highlight results. Table 2 is down here somewhere, but let's take a look there. Can you see table 1? This table has got its own heading. So give your tables a heading and refer to it in text and give it some description of what's in the table. So maybe it's descriptive statistics for the sample for your table. And finally, can you see there's n equals 305? So that's a convention in scientific reporting.
It's the number of participants, right?
It's the number of participants. Okay. So remember we said in our SPSS outputs, we've got that 67 and it's redundant. It shows up over and over and over again. Put that number in your heading instead. So you can get rid of that column, which kind of just takes up space and doesn't really add any value. Put it in your heading instead, and that's conventional in scientific reporting, and it looks good, and it looks like you're a really good researcher, and that's what we want to see.
Right?
That's exactly what we're aiming for. We want you to do well at this. Okay. So that's some sort of conventions in scientific reporting, and your first descriptives table. I think that's quite good. The next thing to think about, we did some correlation results. So we made figures and that sort of thing. Yeah. Should we do one of those? Should we do a correlation statistic and see how we present it? Okay. Where shall we start? Do you want to do energy intake versus expenditure first? Yeah, let's do that. Okay, so same as we did before, go to Analyze, and I'll scroll down past descriptives to correlate, and then roll to bivariate. So for those of you that are new to this, correlation is testing the relationship between one factor and another. Sort of seeing, is one factor associated with another factor. So go to Analyze. Yeah, great. And then scroll down to correlate.
Just energy intake and
And then go to bivariate. You've got to like stay on the track. You go out, then it moves and it's rotate. So one dot. Yeah, click on that. Great. Yeah, hold on to it. Bivariate. Good. Okay. As a reminder, a correlation is sort of a test of the relationship between one factor and another. Did anyone hear that? Was it the falcon? It is falcons that live in our roof. Up here, the peregrine falcon. There's a family of them. They have babies every year, and it's very cute.
Is that where that noise is coming from?
I think so. I think the falcons are on. There's actually a camera on the nest that I will show you after this. You can actually see the. Usually the chicks hatch around this time of year at Easter. Anyway, correlations are tests of the relationship between one factor and another. Okay. So you might say something like, what example did I use last week? Like, as the temperature increases, do we see an increase in the number of ice creams sold? So is there a relationship between the two? So that's what we're going to test now. We're going to see as maybe energy intake increases, do we also see an increase in energy expenditure? Now this one's a bit weird because I can't really justify which is the dependent and independent variable. Maybe that's up to you. I have found from doing this the last 2 weeks that energy intake as the x-axis makes a prettier graph. So let's go with that. We'll just make a nicer looking graph. But we're doing the correlation first. So let's add our energy intake into that box and energy expenditure into that box for your bivariate correlation. You already made your graph. Good. Okay. You got it from last week. Okay, so once you've added those two, we can press OK and you should get your results. Yeah, beautiful. That's exactly what we want. So we press OK and we get this table here. This correlations table. Now this is another one of SPSS's really ugly tables, and not just because it's got this weird like kind of gross 1990s color scheme, and that's not very ideal. It also duplicates the information. You noticed that from last week. So you've got energy intake is correlated with energy intake as 1. Well, that makes sense, because as energy intake increases, so you would expect energy intake to increase because it's the same variable. This doesn't give us, that's not useful. Okay. Energy intake correlates with energy expenditure 0.128. That's useful as an R value. Okay. That tells us the strength and the direction of that relationship. So that's fine. Now notice here, those bottom 3 rows is this information, but in reverse. So you don't need this stuff. That's useless to us, because we've already got. There's your result. Don't need to worry about that one. Okay, so as a pro tip, a mark of someone who's done this test and has no idea what it means will present this entire table, and that just sort of says, okay, you don't really understand the stats. You understand the stats. You've done this. You've done this last week and this week. So don't double up. Just give me that R value there, and we've got a P value of 0.3. So R gives us the strength of the correlation. You've got a table in your in your slides that tells us about strengths of correlation. So we said ours is 0.128, is that right? Yeah? So it's like there, small positive correlation. So as energy intake increases, we see a small increase in energy expenditure. For every unit we go up, right? But not much, very small relationship. And the p-value is 0.3. So is that statistically significant? Sorry,
Is it likelihood that it happens by chance?
yeah, that's one way of saying it. Although if you say it to a statistician, they'll go red in the face and start getting very angry. Yes, so it is probability. So chance does come into it. What it means is it's a hypothesis test result. Okay, this will be easier to. You will definitely understand it when we get to the t-test because I've spent lots of time building up to that interpretation. But very briefly, in fact, can we make the graph and then I can explain it nicely? Okay, so let's make the graph quickly to show this result. Go to graphs, and under graphs there's chart builder. Okay, so you've got graphs and chart builder. Yeah, graph. Yeah, and then chart builder, and then press OK. Yeah, you just agree to their terms and conditions. Don't you worry about it. It's perfectly safe. We just press OK. Okay, so you get this table here, or this window, and we're going to make a scatter plot for our correlation result, because that's the way you usually present a correlation result. So under scatter or dot on this choose from menu, we're going to select scatter and then move that little, I want this one, so this one with little blue dots, click on that and drag it into this file here. So you can follow me if you like. So you click scatter dots, click on this one, click and drag it into the window. Got it?
Yeah.
Yeah? Wow. You haven't done this yet, so this might take you a bit. Yeah? And let go. Got it. Great. Okay. Now we've got an X and a Y axis. So let's add our energy intake. Click on that variable and drag it into the X axis. And click your energy expenditure and drag that to the Y axis. And finally, you'll have a little button there, hopefully in this corner. And you see it says linear fit lines, and you can pick a line for total. So if you make a little tick in this box, just want to see, have you got it? Intake expenditure, click the total line. Click on point 1. Got it. Cool. Alright, once you've done all of those steps, press OK. And we've got a graph. Okay, so I just said this way because the pattern looks nicer this way, but here you go. Yeah, that's okay. So there you go. Okay, so the first thing is you can use your figures from SPSS. Tables, definitely not. They're horrifying. Graphs, these are good. These are nicer than the ones you get out of Excel anyway. You know, that like really horrible orange and blue and gives me the creeps. This is nicer. You've already got headings for the axes. They've got units on them, which is great, and it presents your data very nicely. So you can take this straight and put this into your report. The way to do that is if you right-click on it, you can copy it as an image, and paste it into any file that you like. So you can do that, and you'll get like a nice high def picture of that correlation result. Okay. Now this line here is our line of best fit. It shows us really the relationship between our two variables, intake and expenditure. And you can see it's got a little bit of a gradient, but it's fairly close to being flat. Okay, you can see it's as energy increases, energy intake, we don't really see a corresponding increase in energy expenditure. Right? It's not like everything sort of fits between those two lines basically. So there isn't a very strong directional correlation between these two things. You saw that with the R value. Now your question earlier was about the p-value. Okay. P-values are probabilities. They tell us the probability of the null hypothesis being true. So when it comes to correlation statistics, essentially what we're asking the computer is, is there a relationship between x and y? Our null hypothesis is that there is no relationship between x and y. So we said there is no relationship between intake and expenditure. In correlation, what that means is that our null hypothesis is r equals 0. Because the r equals 0 means no relationship. So what is the probability that r equals 0? When we did our correlation, we got a p-value of 0.3. So 30% probability that the relationship is 0, so 1/3. And that is above our threshold for significance. So non-significant result. I haven't left anyone behind, have I?
Of course you have.
Oh no. Okay.
Because in some results we say there is difference between expenditure energy and
Yeah.
intake, and some results say there is no difference.
So this result we've got here is a correlation result.
So this one say if there is difference.
There's no difference.
No. Well, there's no association.
Oh.
No association.
And that's because the p-value was 30% instead of 0.05.
Yes. And also the R value is pretty close to 0. Okay, so
Can you say again where you see the R value on the, like how?
Top right.
So,
And this
so that's R square. I'll tell you about that in a moment.
Oh,
So our R value is here, 0.128.
Yeah.
That represents, that's pretty close to 0.
Okay.
It's closer to 0 than it is to 1.
Okay.
Okay, so it sort of says there's no relationship.
Also, that would be like that's from the Pearson correlation table, is it?
Yes.
Okay.
Yeah. So it's the Pearson. So here's our interpretations there.
Yes.
So it's
okay, cool.
small.
Yes.
Okay.
It's the other number.
There, the p-value 0.3.
And how to present p-value? To write the same like siege to tail or
P equals 0.3. Yeah. So there's a good question. How do we present this? Let's go to the literature and say exactly that. Did we? So firstly, can you see here we've got a scatter plot somewhat similar to yours. It's got a few more dots in it, but that's because the researchers collected a bit more information. Your figure has got a heading, right? So this one is figure 2 instead of table 1, and it's got a little bit of a description of what the figure is. Okay, and it's been referred to in the text. Figure 2 displays da 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 da. So the way I would go about answering, how do I present this result? I would say, here's your figure. Figure 1 presents the correlation between energy intake and energy expenditure. The R value was 0.128, and P equals 0.303. Put that in brackets if you want. This is a small positive correlation, but is not statistically significant. So there you've summed up everything we've just done. The reader can see it for themselves.
The p value shows there is no association as well.
Yeah, there's no significant association. Precisely. The other example we have for this is the relationship between energy expenditure and weight. So shall we do that?
Yes.
Yes, let's do that. Okay, so it's the same procedure. This time let's start with the graph and then we'll do the R values. So go to graphs and to chart builder and press OK. And you've got your chart builder again. This time take energy intake out and replace it with weight in the x-axis. So I'll come around and just check you've all done the right thing. But you're getting pretty good at SPSS now, so you should scroll down here.
Yeah, I've got energy.
I reset mine anyway.
It should be expenditure.
Oh, that's insane. Whoa, what have you made?
Interpolate the
Sorry, a bit more than me, but okay, you've got it.
It is extremely difficult.
Okay, and now once you put everything in place, you can press OK. And we should have a graph. Should have a
I
graph.
just realised our scatter plots are looking very different in arrangement.
This one here to that one.
Yeah.
Yeah, I've got slightly different.
And yours is different to mine.
Oh, that's a preview, so it uses example data.
Alright,
It doesn't actually, yeah, all it's doing is showing you you've done something.
Ah.
But that isn't the same pattern you can end up with.
once we press OK.
Yeah, so once you press OK, then you get the actual result. Yeah, good. Okay, so now we've got, can you see, there's your scatter plot.
Expenditure or intake?
You want expenditure versus weight, so that's right. Yeah. And then, yeah, that's expenditure. Oh, what have you got? Okay, go back to by yourself. I would just reset and drag it in there. Energy expenditure and weight. So you've now got your graph. So if you look at this one, apart from where can you see on the top end of the weight, you've kind of, there you've got a bit more scatter. There it's a bit more spread. So if your weight is sort of towards 90 kilograms, your energy expenditure could be anywhere between 1,000 and 4,500 calories. This is a large variation here. But towards the bottom end, we get much less, on average, much less variation. Most people between 3,000 and maybe 2,000 calories. Okay, so that's the first thing. You'll notice for the R square, 0.1. So the R square value is something we didn't talk about on the previous slide, but you can go back and compare it if you want to. R square is a measure of how much spread you see. So an r square that is closer to 1 shows very little spread. R square close to 0 means loads and loads of spread. So it sort of tells us how good is weight at predicting energy expenditure.
Did
So
you say closer to 0 it will be more spread?
yeah, some like that, like lots of scatter there.
And that's because there's no correlation.
It's potentially no correlation, but also it's the time when you sort of say interpret these results with caution. Because what you can do with correlations, basically how the Henry equation works, is if I take this line and I make a mathematical equation to describe that line, y equals mx plus c. C is like my intercept, m is the slope, we've got an r value. So all we need now is an x and a y value, and we can predict for a given weight someone's energy expenditure. That's how the Henry equation works. That's exactly what it does. But where we need to be cautious, if it's in this region, fantastic. Probably a fairly accurate predictor, give or take maybe 500 calories. Fairly accurate. If we're on the top end of the scale, if we predict based your 90 kilograms, and we say you need just less than 3,000 calories, the data actually says you might need that 4,000 or 1,000. We don't really know. Lots of spread. Data is really cool when you get into it, and I understand the irony in standing here and saying cool, but it is fascinating. It can be very interesting, very exciting.
But that dot is showing us the participant.
Yes. Yeah, so that's an actual observation of a participant.
But do you think Sean, you know the
Oh wait, I'll come to you. Just
That
sorry.
means that participant who got 90 kilos is taking just is spending just 1,000 calories.
Yeah. Perhaps they're on an extreme cutting diet.
No, but just the metabolism.
No, but it could be accurate because,
Just
for
with the
example,
metabolism is going
I
to be high.
I ate a lot of food the night before I done my testing, so the following day I had hardly any food to eat.
Yeah.
So that could be accurate for one day,
So
right?
that's
Observation.
expenditure.
Also
Yeah.
bring the average into a lower.
I don't think so, because just with the in resting, you're going to spend more than the.
Yeah.
I think
Just on the resting,
they just
you know?
put wrong data. This is some like
A person like me, just resting, I spend 2,000 calories. The person with 90 kilos is going to spend.
Your resting metabolic rate.
No, per day. The
Oh,
whole
yeah,
day.
total. Yeah.
Yeah.
So your physical activity
With
rate might be higher.
with the exercise with the double bar.
Yeah. Yeah. But this, remember, is based on a prediction. Remember, this is based on a prediction equation. So that same inaccuracy is potentially there. Same pattern we're seeing here sort of repeats. So there you go. So you had a question?
Yeah, I just
Yes.
want to ask about the graph. When creating that graph, it's not better put weight on that line and then energy expander on the bottom.
So swap it
Because-
like that?
Yes, because then I think weight more depends from your energy expander than energy expander from our weight. You know, when
Yeah.
we have
Yeah.
our energy expander is higher, then we can be slimmer or fat. It depends, yeah. But how much energy we're using, it not depend about the weight. I think so.
I think it's a good question. It's something I also was wondering this morning, which is the dependent and independent variable.
Yeah.
I would argue
I
that
think-
we're going to use.
I think that if someone is
this way.
not active, the weight is depend about our active. So maybe energy expander should be on the bottom and.
Yeah. The
But
question.
if it is any like a huge deal with this where we're gonna put, because I for sure if I'm gonna do this, I will use
The other way around,
opposite.
yeah.
So gonna be good or
This is the other graph. You know that the line is.
yeah, but
Yeah.
just weight and.
So I would use it this way around because we're working cross-sectionally with the question we're trying to test is, does weight predict energy expenditure? Like the Henry equation does.
And I think because it was only a 3-day, like looking at the data collection point of view, if 3-day your weight will not fluctuate as much.
Yes, but I think just when we want to compare energy expenditure and intake, it's good like that, like expenditure and intake. But when we want to compare other indicators, we should know that we should probably change that.
Yeah. So it is worth thinking about which is
like
but it's similar to what we were saying here as well. Like on the day, maybe you ran 15 kilometers where you don't normally, but your weight hasn't changed at all. So there's that side of it.
Maybe the period of time is too short.
Yeah. Oh, I agree. It's a good thing to think about.
Sense to just thinking like when I will change, we're not going to compare weight with energy expenditure. So I know that must be like energy expenditure and on the bottom energy intake, but just in case when we have like in the future.
Well, even the intake and expenditure thing. I mean, there it's really you have no idea. I never know which axis to put what on. You could argue either way.
No, for me, straight away it was like on the bottom in energy intake and expenditure on the left. I don't know how just.
Yeah, no, it's good points. It's good points. And these are the kind of questions that are important to ask. I'm sure that we're all thinking, which is good. Are you gonna add? Sorry, you had a question.
I just want to ask, with the extreme results, so whether, an example there where participants 90 kilograms and they expended 1,000 calories, can you comment on this?
I wouldn't worry about that. No. The pattern is the important thing. Yeah. And in your results, you wouldn't usually interpret the result anyway. You would just say, here is the relationship. You wouldn't say why you think you got the results you got. You just say, this is the R value, this is the R square value, this is the P value. And speaking of, shall we quickly calculate the R value for our weight versus energy expenditure? So let's go analyze, and let's go to correlates and bivariates. So go to analyze, go to correlates, and bivariates. It's the same as we did earlier for energy expenditure and intake. So again, take the intake out and replace it with weight. So you've got you're setting up correlate energy expenditure and weight. Weight in intake out. Great stuff. So once you've done that, you can press OK. And some of you have done that already because you're fantastic. Sorry, what do we see now? So, like we said there, we've actually you have an idea of how to interpret this already. This bottom part's redundant because it's the same information as the top and the bottom. So just look at the one. Energy expenditure and weight, the correlation, the R value is 0.32. So the R value is 0.32. And if we go to our interpretations, according to this, is 0.32, is it a no correlation, small, medium, strong?
And it would be small.
Small. 0.32?
0.32.
Positive medium correlation. You'll kind of get that. So, because it's slightly bigger than 0.3, 0.32, so it'll fit there. Okay, so we've got a medium strength positive correlation between weight and energy expenditure. Yeah. And we know that this is statistically significant because our p-value is, it's lower than 0.05. It is 0.008. If you get a fraction, is that smaller, right? I don't know, because it's like you have to work in opposites to normal numbers. Especially when it's getting close to lunchtime, a lot of these numbers get harder to. Yes, certainly, I agree. Do it twice in the morning and then you gotta you just start crying on the inside. Okay, right, so like the other one we did, probably the nicest way to present this is to give us your graph, give it a nice label, say figure 2, the correlation between weight and energy expenditure, and before the graph actually appears, include a paragraph saying what are the key results. So you could say weight was found to have a medium positive correlation with energy expenditure, R equals 0.32, P is less than, or P is 0.08, as shown in figure 2. Show us figure 2, everything's good. Yeah?
Sorry. P value is 0.00.
Yeah. So it's smaller than 0.005. I'm even getting the tongue tie with the numbers. Alright. So we have one more result that you need for your report, and that's your t-test. And this is a nice one. This is a really good one. So let's do that t-test. So to do our final test, we want to compare. We're going to answer our main aim of the study, which is energy intake the same or different to energy expenditure?
So this is second part of the hypothesis.
No, this is the whole thing.
That's because you already ruled that.
No.
Do you know how you had the two hypotheses in the beginning? That was the energy expenditure equals energy intake.
So what we've been doing correlations which are slightly different to this question.
Oh yeah, that's not, yeah.
Yeah, so what we've been doing up till now is really, is there an association?
Yeah.
What this question is asking about is difference. Okay, associations and differences are two different operations in stats. And it's something I often say even to the master's students who feel very apprehensive about statistics, is there are really only three things you can do in statistics. You can describe data and find out means and medians like we did in the beginning. You can look for associations like we've just done, and you can look for differences. And that's it. Those are the three main things. And all the fancy tests, the t-test, the ANOVA, the multiple regression analysis, all of this stuff is just variations on one of those three types. Okay, so we've done correlation, that's testing associations. What we're going to do now is look for differences. We're going to see, is there a difference between this average value and that average value? These two groups, these two variables. So, probably a good reminder, our null hypothesis. The student's energy intake is not different to expenditure. In other words, maybe put more simply, the students are in energy balance. Energy intake minus expenditure equals 0 or very close to 0. There's no real difference between energy intake and expenditure. We're going to take a look at our data and see what is the probability of this. If our p-value is less than 0.05, we say they aren't in energy balance. We reject that hypothesis and instead we say they are not in the intake is different to expenditure. So let's do that. Let's go and do that. If it seems a bit convoluted, don't worry, it will make sense. You'll get this. You'll get this. So go to analyze. And now go to compare means and proportions. And let's go to paired samples t-test. Okay, and you should get a window that looks like this one. And once you're there, I want you to take energy intake and make it in variable 1, and click energy expenditure and put that as variable 2. So your setup should look like that. once you've set that up to look like that, you can press OK. And then we get all the tables. We get pretty much the whole morning's worth of stuff. Yeah, energy intake goes, in variable 1. Oh,
No, because like, just just because number 1.
You appear to have an extra one. Yeah, there you go. That looks good. Press OK now. Okay, once you press OK, you then get lots of results. And this can seem overwhelming until you have a careful look and you think, oh, actually, I know what we're looking at here. So, the first table is really a reminder of the descriptive statistics you got earlier. It's got the mean energy intake and the mean energy expenditure, and the standard deviations of both. You see it's mean intake 1,825, mean expenditure 2,402. At first glance, you can sort of see these look a bit different. They don't appear to be the same. Okay, we're going to demonstrate it with the statistics to say this certainly doesn't look to be the same, right, on average for all of our participants. So there's our descriptive data. Ignore this middle table, go to this one that says paired samples t-test. Take a look there. Can you see it says mean minus 577.2, something like that? Mm-hmm. Okay, if you took 1,825 and you subtracted 2,402, you would likely end up with that number. That's the mean difference, or the difference in means. That's how much of a difference there is between the two. That's the first thing. You can ignore most of the rest of this until you get to these last parts here. Can you see you've got a column that says T, and that's minus 7.27. You've got something called DF, which is 66. And you have a two-sided p-value of less than 0.001. So it indicates very highly statistically significant. Why is that? Okay, we've got a p-value of 0.001. So what we're saying is that the probability that our students' energy intake is not different to expenditure is less than 0.1%. It's a very low probability that this is actually true, that they are in energy balance. So we reject our null hypothesis. Say instead that our students must be not in energy balance. Are not in energy balance. What are the implications of this? Think back to your writing your introduction. What's the first thing you're going to tell us about in your intro? No, the energy balance equation? Yeah. Alright, so what are the implications of this?
Weight balance.
So weight balance. We're saying our we've got, if we take a look there, you take a look at your mean difference, minus 577. Our students appear to be in calorie deficits by almost 600 calories per day. What do you expect to happen to them?
Weight loss.
They're going to lose weight if we carry on like that. Probably quite a lot of it. I mean, that's like a kilogram a week. So that's a lot of weight loss on average. Okay, so that's the practical implication. Questions are, perhaps how did we end up with this result? Okay, remember do you think it's really real that maybe our whole students in negative energy balance? Why do we think we got the results we got?
Because sometimes people are more active specific days of the week.
Okay, yeah.
Sometimes they are not active, like weekend they sleep and relax.
I think
yeah. So there's natural variation in the activity level. Yeah.
I think that it's more explore about like recording food or recording expander, like energy expander, because I found in my one that it's totally crazy that it's 2,000 less than 2,000 which I'm intake my energy intake, and almost 3,000 expander.
Okay, so accuracy.
It was really horrible to check indicator which I should choose. When I'm sitting, doing like, I don't know, reading a book, then going to the toilet, then going to the duty, it's crazy.
It's difficult, and also you make a good point there as well. We use physical activity ratios in 5-minute blocks. So, you know, you have the example of you're going home, you see your bus, you run to your bus, but you run for 30 seconds. Do you put running for 5 minutes, or do you put no running at all? Does it capture everything you've done? So maybe energy expenditure is over-reported here because of those blocks. What else could have happened with our data?
Alteration in what you eat, just making it easier.
Yeah. So actually,
I was very strategic about
it
as well.
So
energy intake underreported.
Yeah.
So underreporting.
Social bias.
So there's and there's lots of literature about that.
Sometimes you forget.
And sometimes you forget. Yes. So there's all those sort of there's all those kind of errors and biases that creep in. You change what you're eating. You know, normally you'd make these really elaborate meals because you enjoy cooking, and that's great. But this week, because you're doing a 3-day diary, you're going to make peanut butter sandwiches because it's easier to write 2 slices of bread and a tablespoon of peanut butter. And so there is that. Okay, there's that. So you've changed, or you've cooked a whole bunch of things, but you've sort of said, I don't really feel like writing down half a pepper, whatever. I'm leaving that out. So there's the recall bias, or you forget. You're in the kitchen, you're making things as you go. You forget that you use this and this and this as ingredients. That can happen. Or you can willfully actually say, you just underreport what you did because you're a bit nervous about maybe what other people think of how much you've eaten or what you've done, even though no one sees that. That might be part of it as well. So all of those factors, so there are potentially inherent biases with the techniques that we've used, the way we've measured the data, all of those are fine, and it's okay in scientific writing to get results like this as long as we can explain why we think that result is the way it is. Now, if you had to do this study again and you wanted more accurate results, how would you go about doing that?
More days.
Okay, more days. Yeah, so your point was like the weekend is different to the weekday. What's the gold standard for 7 days? Can you see how your introduction, your discussion match now?
Yeah.
You've introduced what is the 7-day weight-free diary as the gold standard. Your discussion, you can say, okay, here's a limitation where we did. What is the solution? How do we measure it more accurately next time? 7-day weight-free. What else can you do to improve the
more accurate taking data, collection data?
Sorry, those two at the same time. We start there and we can come back here.
I think that Shadow was saying that for the energy expenditure, we can use the double water label.
Okay, yeah. So we've predicted the energy expenditure, and what we could do is actually measure through indirect calorimetry the thing. What are you gonna say?
A more accurate way to collect data.
So more accurate. So and then you've got an energy expenditure.
Which was the method used when they kind of double whatever you're eating? They test
Yes, there's another one. I think it's not it's the duplicate diet. Duplicate diets, so everything you plate up, there's a second plate, and then they take that to the lab and they burn it and they see how much energy is in it. Did you do that? Have you done that?
No, but we just learned about it.
You've learned about it. Okay. So there's another way. So maybe that's a nice suggestion. Good one. There was something else I wanted to say on that last point that I've forgotten, but it's fine because I think we've.
Give a more narrow data set to participants to use for PAR levels, because I think if you hit at this.
Possibly, yeah. So there's that accuracy in the.
I think instead of putting the box for like 5 minutes, you just take a list of our activities
Oh, actually, yes. What I was going to say is related to this. So as many of there are limitations to what the technique we use with the 5-minute blocks and the physical activity and predicting. When SACN sets your EARs and your RNIs, your requirements for energy and protein and those sort of things, but focusing specifically on energy here, they use the factorial method, same techniques you guys have used. So there is a external validity to what you've done. So while we say, okay, we're not sure exactly if this is right, you've used the same techniques that the government uses to set everyone's nutrient requirements, which is interesting. So there's an external validity. You can compare your results technically to what SACN produces from the NDNS to set, there was like 1,940 calories for men and for females, and 2,470 for men or something. That's what they end up with. Using the same thing. They calculate what is the average person's energy BMR from a Henry equation, or Schofield, or whatever they used in 91 where they did it, and then they multiply it by a physical activity ratio. They use a PAL of 1.4. So there's validity to what you've done in a sense as well. Yeah, their class is all as sedentary. Yeah. Which is also why, if you're thinking about individuals' energy requirements, this is the last thing, absolute last thing. You can see not many of you actually, and this is a full female data set, not many were sort of there at the 2000. Because remember, that government 2,000 calories is an estimation. It's going to meet half the requirements of the population, or it's going to meet the requirements of 50% of the population. Look where everyone is, much higher. People need more energy than those things. But that's another story for some other time, because we've gone over time now. You're taking the steps to become